Geometry assurance is about analyzing the effect of variation, improving the robustness, which means decreasing the concept sensitivity to variation, and knowing what tolerances to tighten when necessary. Tolerances are the key to mass production, but tight tolerances means high cost. If we can improve the robustness of the concept, we can create better quality without increasing the cost. So let's show the concept of geometry assurance on a real product, the rear lamp of a car. In this case, we are interested in the relation between the rear lamp and the rear window in this corner. So it's a flush dimension. In my model, I have already defined the expected variation and the locating schemes for all the individual parts. So now I will do a variation simulation. In the variation simulation, I use Monte Carlo simulation to run 1,000 iterations, meaning I create 1,000 cars. Ready. So here we can see the output variation in this critical dimension that we are looking at, the relation between the rear lamp and the window. And we can see that we have a tolerance for this critical dimension, an upper dimensional limit, a lower dimensional limit, and we can see that a lot of the distribution is outside this tolerance band. So this is not very good. We can also see that 6 sigma, which is a measure of variation, is 8.92, which is not so good. Let's see how this looks. So this is how it might look on a real car or a population of cars. This is what we can expect in worst case. Not so good. So what can we do? Let's check the robustness of the concept by doing a stability analysis. In the stability analysis, we vary the locators for each part, and we see how that variation propagates and amplifies. So in this case, we can see from the color coding that we have an amplification of 9.46 times the variation we put in the locators. We can see that the sensitive area is near to where we are looking, where we have the critical dimension. So if we check our locating scheme and we check the primary locators A1, A2 and A3 that are supposed to describe a plane, we see that the locators are not spread out enough, and we see that we have no locators near to the critical area. So let's see what happens if I move one of the locators. Let's move locator A3 and put it somewhere here. The color coding is updated, and from the blue color we see that we have a much more robust system. Let's do the Monte Carlo simulation again and see what effect that had. I do 1,000 Monte Carlo iterations. Look at the critical dimension. So now we see that almost all of the population is inside the tolerance band. We have 6 sigma, 6 standard deviations of 3.76, which means that we have decreased variation by more than 100% by moving this locating point. Much better. Let's see how it looks. We are going in the right direction, but we are still not satisfied. So we have improved the robustness. What can we do? Maybe now we can try to tighten the tolerance to reduce variation in the critical dimension even further. But what tolerance should we tighten? We have a lot of tolerances on all the parts, and they contribute differently to the critical dimension. So we want to tighten the tolerance that contributes the most. So we do a contribution analysis to find out about this. In the contribution analysis now, we see that 66.9% of the variation in this critical dimension comes from the uniside and a specific tolerance that we have defined for this part. So let's see. We have 2 millimeters variation defined for this part. Let's see what happens if I change that. I reduce the 2 millimeter variation to 1 millimeter for this. Okay, so we do the Monte Carlo simulation again. 1,000 cars. Now we can see that 6 standard deviations are 2.68. So we reduced it even more now. Let's see how it looks. Much better. So maybe we can live with this. So now, when we are ready with a rear lamp, let's do the same job for the front end of the car. But that's another story. Thank you.